Welcome to the fascinating and sometimes terrifying world of medical parasitology. Today, we are going to master everything about Xenopsylla cheopis, commonly known as the oriental rat flea. This tiny insect is not just a household pest. It is the exact biological vector responsible for the Black Death, a pandemic that wiped out a massive portion of human history. By the end of this lecture, you will understand exactly how this microscopic ninja operates and how we mathematically predict the outbreaks it causes. Let us dive in. To begin our journey, we must understand what makes this specific flea so historically significant. While we have all seen common fleas on dogs or cats, Xenopsylla cheopis prefers to feed exclusively on rodents. Imagine a tiny, wingless, blood-sucking ninja that can jump incredibly high and hitchhikes on the backs of rats. Why does this matter to us? Because this specific insect is the primary biological vector for some of the deadliest diseases in human history, most notably the Black Death. It bridges the gap between infected wildlife and human populations. Now that we know its historical impact, how do parasitologists actually identify this flea under a microscope? Xenopsylla cheopis belongs to the insect order Siphonoptera. The most crucial diagnostic clue is actually what it lacks. Unlike common cat and dog fleas, it completely lacks both genal and pronotal combs, which are thick bristle-like structures around the head and neck. Furthermore, if you are looking at a female specimen, you will see a distinctively shaped spermatheca, or sperm receptacle, that looks exactly like a tiny comma. Like all fleas, it develops through complete metamorphosis: egg, larva, pupa, and adult. Let us visualize these morphological features clearly. On your screen is a detailed anatomical diagram of Xenopsylla cheopis. Notice the rounded head on the left. It is completely smooth, lacking those thick, bristle-like genal and pronotal combs we just discussed. Moving down from the head, you can see the specialized piercing and sucking mouthparts used for feeding on blood. At the back, observe the robust, elongated hind legs that allow it to jump massive distances relative to its size. Finally, look near the posterior end of the abdomen. That small, distinct, comma-shaped structure is the spermatheca, confirming this is a female specimen. Having identified our vector, we must now look at the microscopic cargo it carries. You might be wondering why we care so much about one specific type of flea on a rat. The answer lies in the bacteria it transmits. This flea is the primary biological vector for Yersinia pestis, the deadly bacterium responsible for the bubonic plague, as well as the bacteria that cause murine typhus. When this flea feeds on an infected rat, it ingests these pathogens. Instead of being digested, the plague bacteria survive and begin to multiply rapidly inside the gut of the flea, setting the stage for a gruesome biological mechanism. This rapid bacterial multiplication leads us to one of the most fascinating and horrifying mechanisms in parasitology: the blocked flea. As the Yersinia pestis bacteria multiply, they form a solid, sticky biofilm plug in the flea's proventriculus, which is essentially its throat. This creates a physical blockade. Because the flea can no longer swallow blood, it begins to starve. Driven by starvation, the flea frantically bites new hosts, including humans. But since the blood cannot pass the blockage, it bounces back, repeatedly regurgitating the trapped plague bacteria directly into the fresh bite wounds. This is how the disease spreads so efficiently. Let us look closer at the internal anatomy to truly understand this blockage. Here we have a cross-section of the flea's foregut. On the left, you see the esophagus, where blood enters during a bite. However, right at the junction before the midgut, you can clearly see a large, dark mass. This is the bacterial plug of Yersinia pestis. Notice the arrows indicating the flow of blood. The blood enters, hits this solid biofilm wall, and is forced backward. This visual perfectly illustrates why the starving flea regurgitates infected blood back into the host, making it such a devastatingly effective transmitter of the plague. Now that we understand the biological mechanism of transmission, how do we stop it? To predict and prevent plague outbreaks, epidemiologists cannot just look at individual fleas. They must look at populations. They rely on mathematical metrics to quantify the exact risk level in a given environment. By measuring the density of the vector population, which are our fleas, relative to the host population, which are the rats, we can anticipate disease transmission before it actually happens. This transition from biology to mathematics is crucial for public health officials to deploy resources effectively and save lives. This brings us to our first critical mathematical tool, the specific flea index. Conceptually, this formula calculates the average number of target fleas living on a single rat. Let us break down the symbols. F represents the specific flea index itself. X stands for the total number of Xenopsylla cheopis fleas collected from the trapped animals. Finally, R represents the total number of rats that were examined. Think about the physical relationship here. If the value of X increases, while R remains constant, the index F will rise. A rising index indicates a growing flea population and a much higher risk of a plague outbreak. Let us put this formula into practice with a real-world scenario. A medical team captures 50 rats and collects 120 total fleas. However, only 85 are identified as Xenopsylla cheopis. What is our index? First, we must carefully select our data. We only use the specific vector count, so X equals 85. We ignore the other 35 fleas because they are poor vectors. Our host count, R, is 50. We substitute these into our equation, dividing 85 by 50. This yields a final specific flea index of 1.7. This means, on average, there are nearly 2 oriental rat fleas on every single rat in this village. So, we have calculated an index of 1.7. But what does that number actually mean for the people living in that village? The specific flea index is a pure ratio, an average count. In epidemiology, a specific flea index greater than 1.0 is traditionally considered the critical threshold for a potential bubonic plague outbreak. Since our calculated value of 1.7 is significantly higher than this threshold, the village is currently at a high risk. This mathematical result dictates immediate real-world action, such as dusting the rat burrows with targeted insecticides to protect the human population. Beyond just counting fleas, we must also account for the frantic behavior of the blocked flea. This is where the daily transmission risk factor comes in. This formula models how aggressively the disease might spread. T represents the total daily transmission risk factor per rat. We calculate this by multiplying 3 variables. F is the flea density we just learned. Lowercase b is the behavioral biting rate, which skyrockets when the flea is starving. Lowercase p is the biological success rate, the probability that a single bite transfers the bacteria. If any of these 3 variables increases, the overall transmission risk scales up proportionally. Let us see exactly why the blocked flea is so dangerous by calculating this risk. Imagine a village with a high flea index of 2.0. A starving, blocked flea bites a host 5 times a day, and the transmission probability per bite is 40%, or zero point 0.4. We substitute these values into our equation. First, we multiply the flea index of 2.0 by the 5 daily bites. This tells us a single rat receives 10 flea bites every day. We then multiply those 10 bites by the zero point 0.4 transmission probability. This yields a final transmission risk factor of 4.0. This means we expect 4 successful infectious transmissions per rat every single day. We have covered a tremendous amount of ground today, moving from microscopic anatomy to public health mathematics. Let us reinforce our 3 most important ideas. First, Xenopsylla cheopis is uniquely identified by its lack of genal and prenodal combs. Second, the gruesome blocked flea mechanism caused by Yersinia pestis turns this insect into a starving, frantic, and highly effective biological weapon. Finally, by calculating the specific flea index and transmission risk factor, we can mathematically predict danger zones. You now understand both the biology and epidemiology of this world-altering vector, empowering us to stop outbreaks before they devastate populations. Excellent work.